All right, everyone, let's get started for the afternoon session. Okay, so this morning you all learned about directed graphs, probabilistic graphical models, which are a way of representing the structure between different components in a model. And this afternoon, we're going to be talking through some of the more practical applications of that, which is hierarchical Bayesian analysis. If throughout this afternoon's talk, you hear me say hierarchical Bayesian modeling or HBM or HBayes, it's all the same thing. So don't let those, differences in jargon confuse you. I'll also say that HBayes is really, really subtly tricky. It's one of those things that's kind of simple in concept. And probably as I'm going through the lecture, you'll kind of phase through like thinking like, oh yeah, I got this. This is simple. And then wait, I have no idea what Greg's talking about. So kind of let those waves of understanding and misunderstanding wash over you. I know when I was learning this, it took me several passes to get through it. So I'm going to do my best to, give this lecture so that there's something for everyone, no matter what level you're at. But it is a pretty subtly tricky topic. So if you have questions as we're going, please don't hesitate to speak up and ask them. I'm sure if something's confusing you, it's confusing at least one other person in the room. All right, so all that being said, just to remind you of the framing of all the talks I'm giving this week. So what I really want to impress on everyone is that whenever you're building any sort of model, you're making a lot of choices, both implicit and explicit. Yesterday, we talked a lot about the machinery that you use when you're trying to draw samples from the posterior, the specific sampling techniques. Today, we're going to focus on more of like the physical parts of the model. So these are, to me, some of the most fun parts of doing science, is you get to think like, okay, what actual physical processes do we want to include in our model? Is there physics that we can approximate as negligible? Are there things we want to include or exclude? And do we want to consider the relationships between different objects within our sample? And so hierarchical modeling is, I'm a complete evangelist for it. I think it's often the best way to do things because basically any problem you have, there's going to be some sort of hierarchical structure between the data. So far, we've pretty much treated everything as just, you've got a whole bunch of measurements, you draw them from all the same pool, but in the real world, that's not usually the case. All right, so to remind you of Bayes' theorem and the notation that I'm using, these are all of the components. Right, yesterday, we focused on drawing samples from the posterior in the case of MCMC methods. And then for nested sampling, that's focused on calculating the evidence, which you can then use to generate samples from the posterior as a byproduct. So one framing of hierarchical modeling that I have really felt is instructive to think about is what you're doing is you're self-consistently modifying the prior. In everything we've done here so far, probably in all of the modeling you've done outside of here, you've started and you've just chosen a prior and then fixed it, and it's been totally static throughout the problem. And maybe you run your model a few different times, you try different priors, but at the end of the day, you're just choosing a prior and then that's fixed. But when you do that, information is only flowing in one direction. It's only flowing from the top down, from what your prior knowledge is, your assumption about whatever population you're drawing from, down to the individual members of the population. But the beauty of hierarchical modeling is it allows information to go both ways. So not only is information flowing from the population down to the individuals, but it's flowing from the individuals back up to the population. So if, say, for example, you're trying to infer, chemical abundances of 20 different stars, you can pool the information and the stars learn from each other, and you're able to get tighter constraints on the individuals, even in the case of noisy measurements. So the way that comes into Bayes' theorem is we've got these hyperparameters, alpha. And I'm going to be consistent here. I'm always going to use theta to represent the parameters that are, the parameters you've thought of. These are the things that we actually care about inferring. The they describe the individual objects. And then the hyperparameters are at that next level up that describe your prior. Any questions so far? I've just given you a lot of information. Okay, cool. So as always, there is still an implied model that goes into Bayes' theorem, right? We've still had to choose some sort of functional form for our prior distribution. So whether we say, our prior is a Gaussian distribution, then our hyperparameters are some mean and some scale factor. Maybe we say the functional form of our prior is a beta distribution, and then we've got the two quantities that describe the beta distribution. So you're still making some choice that's fixed, which is the functional form. But rather than at the top of your modeling, choosing exactly point values for what you want those hyperparameters to be, which describe your prior distribution, we are, as we're modeling the parameters theta, as we're sampling from those, we're simultaneously going to be sampling our hyperparameters alpha, and that lets the prior grow and shrink in a way that's going to ultimately describe the population level distribution. All right. So that's the conceptual introduction. And what I want to do is walk through what's probably like the classical problem of hierarchical Bayesian modeling, which is the 8 schools problem. This is from the Gell-Mann textbook that I recommended yesterday. I think Brian sent out a PDF link there. So there's a chapter on H-Bayes in there that's well worth reading, and it goes through this there as well. So that's another way you can see the same problem presented. Okay, so here is the setup to the problem. Let's say that we have 8 different schools, and students from the schools all engage in a test prep program. And at the end of the test prep program, they all take their exam, and we record the average improvement per school, delta S, and the uncertainty on that mean, sigma. Right? Just to give you a little bit more jargon, a lot of the work on H-Bayes was developed by Gell-Mann, who came more from a social sciences background. You'll often see this called like the treatment effect. So I've avoided using that language here so that I can use language that's more familiar to physicists. But if you see in anything else you're reading treatment effect, that's referring to what that delta S is. Okay, and so here's our summary of the data. Right? Each school has a mu and a sigma sub-mu. Same data plotted in a histogram or the bar chart on the left. Right? And you can see that the score improvement for school A is quite a bit higher than the other 7 schools. Right? And so the question we want to answer is whether this measured effect size can be appropriately attributed to the test prep program, right? Okay, so there are 3 ways, at least 3 ways, but there are 3 ways that we can choose how to model this data. The first is the independent method. That's what we've already done. Right? This is usually the most straightforward and obvious way to do things. You've taken each of your individual members, you've calculated the mean of the measurement and the uncertainty on the measurements, and then we have these 2 vectors, and we can plot those in our bar chart. Great. We have some results that seem plausible, but maybe a little bit noisy. The next thing you could do is you could do what's called a pooled model. And this is the other end of the extreme. Rather than taking all of the individual members and analyzing them completely independently, we just take everything and throw it into one bucket, and we calculate just the mean and the uncertainty on the mean for the entire population. So you can calculate this analytically. You just do, the weighted mean and the weighted uncertainty of those on the left. You guys can do that as an exercise for yourselves later if you'd like, but this is what it comes out to. So these are, again, the 2 extremes that we can deal with, right? Fully independent or fully together. But, right. Okay, so just to do a little bit of intuition building before we get into the hierarchical model, right? We asked ourselves, can we attribute this treatment effect, the measure effect size for school A, to the test prep program? You can calculate this analytically if you assume everything's drawn from a Gaussian, et cetera, et cetera. I never find those analytical proofs all that intuitive. I find bootstrap tests just a lot better for getting a feel for what the data is doing. So if you just draw random samples from those vectors based on the uncertainties, and you plot the minimum and the maximum observed delta S, you can see that over 1,000 trials, we never achieve a score improvement of 28. And that suggests that whatever is going on with that school A, probably it wouldn't be appropriate to attribute the score improvement to what this test program doing. There's some sort of confounding variable or something else going on. Okay, so here is how we actually build a hierarchical model. First, the first assumption we're going to make is that all of the schools are drawn from the same overarching population. So this is the simplest hierarchical model we can build, which is just a two-level model. There's a population level, and then there's the individual levels. And we are going to then also assume that the population distribution is a Gaussian. So we're going to say for our population, right, everything's drawn from some Gaussian distribution with a certain mean, alpha sub mu, and a certain width, alpha sub sigma. That's the notation I used, right? I want to be consistent. Yes, great. Okay, so this is our population, and then we're going down to 8 schools, which are going to be drawn from that, right? And as we fit this model, we're simultaneously going to infer where the individual schools are and what the overall spread is and mean of the population. And each of these are themselves not actually going to be just point estimates. Each of these are themselves going to be some distribution that has a spread. I see a lot of nodding heads. Any questions? Okay, yeah. Yeah, so we've got this overall population, right? And the population has some mean and some spread. And from that population, we're going to draw score improvements for the 8 schools, right? But because we're going to run this through an MCMC, with each step of the MCMC, we're going to not only adjust what the mean and the spread are of the population, but also what the individual values are. So at the end of the day, we're going to have, many, they're not going to be quite Gaussians, but mini Gaussians for each of these 8 members, and then one broader Gaussian for the population. Okay. And so we've assumed that our population is a normal distribution. We can take any functional form we like, and in practice, it's probably a good idea to try lots of different functional forms and make sure you get qualitatively the same answer. But a normal distribution is a good default. So we've got a normal distribution that is alpha sub mu and alpha sub sigma. All right. And then we need to, on these hyperparameters, define what distributions we're drawing those from, right? So those are our hyperpriors. So what we're going to say is we're going to say that this alpha is drawn south from some normal distribution, and that's going to have sigma and mu. I apologize that we're starting to pull double duty and then triple duty on mu and sigma, but that's just good. That's just what happens when we use Gaussians a lot. Backwards. And then we are going to say that our sigma parameter, our scale parameter, we're going to draw that from a half-Cauchy distribution. What, equals 2 or something. We'll set some appropriate number on it. Yeah.
What's the reason for choosing those two?
Yeah, so for the mean, right? You can kind of see that it would make sense for you to suppose it's at some central value and then there's some spread in either direction. And that, if we think about the central limit theory, probably if we're trying to figure out what the mean of the population is, saying that there'll be some Gaussian uncertainty on that mean is a reasonable estimate. The other answer is simply, normal distributions are easy to work with, so it's good first try. A Cauchy distribution has a long tail and infinite variance. So it's a good default choice for scale parameters because it has reasonably good behavior near zero, but then you're not a priori ruling out very high values in the tail. And you want to choose a beta value such that maybe 95% of your expected values are within close. You kind of play around with them. The good thing is for a lot of hierarchical problems, because you're now one layer removed from quantities you care about, assuming that what you care about is inferring theta, you're a little less sensitive to your exact choice of hyperprior. Now, if what you care about is inferring the population distribution, you do really care about the functional form of these hyperpriors. But my advice here is going to be the same as always. Try a bunch of different things, make sure you get the same result as long as you're doing something that's reasonable. So all of that makes sense? Okay. So that's our hierarchical 8 schools model. The first problem on the problem set today is going to be for you all to actually run this yourself. So you'll get a chance to build this model and try sampling from it. But when you do that, here's what you get. What you may notice is that everything on the right looks like it's very, very close together. And that is a property of hierarchical modeling called hierarchical shrinkage. Because all of the individual members of the group are learning from one another, they're all drawn back towards the population mean. They shrink towards the population mean. And so you're able to get much tighter constraints, right? Not only are they all drawn towards the mean, but you can see the uncertainties on the individual members are smaller as well. Eyeballing that, it looks like maybe they shrank by about a factor of square root of 8 or square root of 7. But, we shouldn't always default to those Poisson uncertainties like we always do since we deal with photons. But all of this makes sense to everyone? Yeah. Yeah.
Just an example.
Mhm.
Let's say for the first bar,
Mm-hmm.
so the shrinkage depends on whatever value you get initially, like larger the value it is, more the shrinkage.
Generally, yeah, if it's like the stronger outlier is going to be pulled more towards the mean than the other problem, than the other members.
So whichever is closer already won't shrink as much. So the larger ones are something.
Probably, yeah, but it'll be a little bit on a case-by-case basis. If, for example, the uncertainties here were like tiny, tiny, tiny to begin with, and that would probably be a good example to have run for you guys. Say the uncertainties here were very, very small. You would have been more confident to begin with in that measurement, so it would have shrunk towards the mean less. But that would have also influenced the population, so you would have gotten a broader distribution of everything. So all of these points, they contain the information about all of these measurements. Okay. Any other questions? All right. Like I said, it's both conceptually kind of simple and also like really, really tricky at the same time. So yeah.
Are we saying that school E did worse despite this about 8% change or 8 change in score from this the test prep program?
Yeah, that's That's a really good question. Yeah. Yeah, the interpretation of this is pretty subtle. What we're saying with this orange plot here is that this value of, say, like 7 or 8 points per school is what we can attribute to the test prep program. Right? So each school, we can attribute about 7 or 8 points, plus or minus 4 or 5 points to the test prep program. And whatever other variability we saw in the actual measured mean is due to something else, whether it's just random fluctuations or differences in students or teachers or whatever. Okay. Yeah.
If you applied a similar hierarchical model where you have like stuff that are correlated but not causative, like there's a lot of, you know, kind of come up with it, would this also attribute fluctuations in the independent analysis to some, like, I know I don't know an example that probably make this a better question. I'll reformulate this and
Okay.
again later if I.
Sure. Yeah, let that marinate and we'll come back to it. Any more questions on the 8 schools model before we move on to the next problem? Okay. So now let's go a little bigger. Rather than talking about 8 schools, let's talk about 5 school districts. So same setup. We have a whole bunch of students that are taking test prep program. At the end of the program, they get exams. We see what the change in the school was, in the score was. And in this case, we're also going to monitor and see how effective studying was for these students. Right? On the x-axis, you can see hours studied, y-axis, the change in score, and the different colors. Each one is for a different district. Okay, and I know these colors aren't all 100% colorblind friendly, so you can also eyeball it within a certain district. The uncertainties are all about the same. Okay, so I'll open up to the group. What are the different ways that we could model this data? Linear? Okay, can you say a little more?
Well, besides the orange data, like if you take that out, it seems like a flat line can describe, or a slightly sloped line can describe the overall pattern.
Okay, so we could, reject one of the schools, just assume that that's an outlier. That's one way we do it.
Yeah.
Yeah. How else might we do this?
We could.
Yeah.
We could feed each district independently or all of them with the same. Oh no.
Yeah, exactly. We could treat each of the districts independently, or we could just fit one functional form to all of them. You mentioned a power law. Let's keep it simple. We're just going to stay with lines for now. But yeah, those are the first 2 things that you should try. Just treat everything independently, fit everything with one functional form. Even if that's not what you think you're going to do for your final model, it's still good for intuition building. And I also find that as you're building your model, it's a lot easier to warm up to a full hierarchical model by building those simpler models first and then modifying them. If you just start right away trying to build a hierarchical model, often it's too complex, you make mistakes, and it gets really tricky to do. So let's start off with just the absolute simplest thing we can do, a pooled model, and fit a line, and this is what we get. How does this look to you guys? Yeah, I agree. I agree. Yeah, you're not going to insult me if you tell me it's not a good fit. It's not supposed to be a good fit. Yeah, I'm glad that was everyone's response. It tells me you've got a good intuition for what's supposed to be going on. It's a crummy fit to the data. You can just tell by eye. And so either that means we need some different functional form for this, or we need to consider the fact that everything was drawn from different districts. One other point I'm going to make, we can trust these uncertainties on the data. So in this case, let's just say those are correct. Okay, so our pooled model is not great. So the next thing we can do is fit an independent model. And here I've overplotted with the dashed lines, the ground truth, right? So these were generated from independent linear functions for each of the schools, but I built them hierarchically, so the slopes and intercepts would be related. I can see two things that I don't like about this fit. Maybe you guys can see more. Can anyone see anything that's not great about this model?
Outliers are disregarded, those 20.
You're talking about the high orange and blue point?
Yeah.
Yeah, so those don't look like they particularly fit the data, which is definitely something to investigate. With low number statistics, it's not necessarily a problem. Sometimes you can just get an outlier, but it's worth looking into in a real world problem. Yeah,
Actually, never mind. I'm so sorry.
that's okay. Yeah.
Sorry, can you explain the dashed versus the solid?
Oh, the solid line is the posterior results I get from running an MCMC. The dashed lines are the ground truth. Yeah. Yeah, I was pointing to you in the red in the back, but yeah. Yeah, it's a good observation. That wasn't something I thought of, but they're basically the same. They look like they have similar uncertainty, so maybe there is something linking them. Yeah.
I'm not sure if my understanding is correct, that we're trying to build a model of how, given how many hours studied, what is the change in score, then this is not really saying as much, especially when the hours of study represent 4 or 5, because we will have 2 answers for one. But
Yeah. You're right. We will have 2 answers for one value, because we're assuming that it's not just the hours studied. There's also differences between the schools.
right, and that makes
Yeah,
sense logically. I was just not sure if we want to keep asking for that information, or we just want to build a more generalized model.
Yeah, so in this case, what I was going for is we want how much each score improves per hour studied for each school,
Okay.
right? But thinking about those questions of what is it we're actually trying to measure, I hadn't explicitly said that. So that's a great thing to point out. We want to explicitly say, what do we want to measure? So yeah. Yes.
Splitting them all up like this, you have a really short baseline for a lot of them. Like for the school in red, you have very little variation in the x-axis. So it's hard to say much about how much the change in the hours studied changed the score, since there was very little change in the hours studied.
Yeah, exactly. Absolutely. And that's one reason from the outset, we probably wouldn't want to model it this way. That's a very important consideration, is what's your baseline. Yeah.
Building on what you say. So if you look at the blue one and the far right red one, they're like clumps, you know what I'm saying? Like this 1 point closer to 5, and all of them are very close to 4. And then there's like a bunch of them close to 3 with the blue one of them is far. And we're trying to fit like what is going on in between. You know what I'm saying?
Yeah, the data is kind of like clumpy and clustered. And yeah. And these are all motivations for why we want to use a hierarchical model, right? We don't have that many data points within a school, or they're not covering a large baseline. We need to get more information from somewhere, and building the hierarchical model is one way we can learn about that. So you guys thought of a lot of great issues with these models. Let me tell you the 2 things that I saw as the big problem. One is this blue line, that it has a negative slope, right? Which doesn't really make sense. That's telling us that, yes, sometimes you can study more and you do worse. Let's assume that you should at least have a flat line or an increasing line for if you're studying more. Right? So not necessarily a valid assumption, but this negative line does seem kind of iffy to me. The other is this orange line, right? That what this model is telling us is if you study for less than an hour, your score is going to go down. Not necessarily wrong, but just, taking a step back from all the technical machinery of building the model, you want to always keep your eye out on the ball for, what's the simple thing you're trying to do in terms of the real world, right? as you study more, you expect your score to go up. Right? That's our implicit prior in all of this. And so when we get this orange line and the blue line, it doesn't necessarily mean it's wrong. But for me, when I see those, my spidey sense starts to tingle and I say, something's probably not quite right here. Okay, so if we run everything through a hierarchical model where, let's build that. So we've got a line, which is described by slope and an intercept, right? Y equals mx plus b, back to algebra 1. All right, and so what we're going to assume is that each of our 8 lines, they have a slope and an intercept that are related by the population. And again, for simplicity, let's just assume those are drawn from Gaussians. So we're going to have some population Gaussian of sigma sub m and mu sub m. And then for each of the 5 schools, well, 1, 2, 3, 4, 5. And same thing for the intercept. Again, I'll have some Gaussian where it's got some population mean, some population width, and our 5 individual members. Again, each after we run our MCMC, having some spread. That all makes sense? So we'll say that M is drawn from a normal distribution, sigma sub m, mu sub m, and B is drawn from some normal distribution. And yeah, I wrote these backwards, but you guys get the idea. So when we do all of that, this is what we get. Right? And once again, you can see the shrinkage in the parameters. What you'll notice now is all of these lines look like they have much more similar slopes. Right? And you may also notice that everything looks like it's been pulled to the value of these green points. And that's what we want. That's a feature of hierarchical modeling, is we've got this school, which not only has the smallest uncertainties on the measurements, but also a longer baseline, which is exerting a stronger influence on the population. Right? Assuming that we can trust our measurements, which I told you we could, then this is good. Everything has shrunk to this value. And then you see some also some shrinkage in the offsets, although it doesn't appear to be as drastic. Right? And yeah, this blue line, we are further from the truth than perhaps we were before, but it seems a little bit more plausible. And, you know, in a real world problem, you're not going to know what the answer is that you're going to get. So, you know, in most ways, this hierarchical model gets closer to the truth than our other models did. In this one case, it does a little worse, but that seems like a reasonable trade-off to me. So, any questions on all of this? Yeah.
So going from 8 schools to 5 districts,
Mhm.
zoomed out, but in both cases just have like the 8 levels.
Yeah.
District, and then school becomes the individual.
Exactly.
You could have added a third to talk about this.
Yes, if within each of these different schools, we had like a whole. Yes. Sorry.
It depends what question.
Right, exactly. Yeah. And someone had suggested maybe these two are related. We could have added another layer saying, let's assume that these two are maybe drawn from, a district in one part of the state, and these three are drawn from another part of the state. So you'll have to look at like the context of the problem. Yeah.
What's the sigma for a slope?
What's the sigma for the slope?
Yeah.
I didn't write it down on the slides. I can check the code that I ran after this and let you know, but pretty small. You can see by eye, pretty small.
Yeah, but like that small sigma is constrained by the data or that came from the assumption.
Yeah, it came from the data, right? The assumption that we've made is the functional form is a Gaussian, but once we make that functional form, we have fit for these, the sigma sub b and mu sub b simultaneously with fitting what we think the prediction is for each of the individual points. Cool. All right, so in the last 5 minutes we have left, there's just a couple of things that I want to mention to you guys. These are complicating details and things that I want you to be aware of that they exist. Don't worry about necessarily applying these during the problem set, but they're important things to like at least have heard these words. So one is this idea called off-centered parameterization. There's a problem you get into a lot of the time with hierarchical models, and it's not unique to hierarchical models. It can arise whenever you have any sort of conditional structure between variables. They're called hierarchical funnels, where MCMC samplers can really, really struggle to explore deep in the funnel. Right? So on the top here, you can see these are the samples that you would get by running an MCMC routine with a straightforward naive parameterization, where you draw y from this normal distribution, and then you draw x conditioned on y. You can see here, this is closer to the truth, right? Where the funnel is narrowing as y gets smaller and smaller. That's this quantity here. Right? But if you do this off-centered parameterization, now you're no longer feeding one variable into the draw for the other one. So we're going to draw them each independently from these standard normal distributions and then scale them. Right? So rather than trying to directly draw samples from this very narrow funnel, which has strong curvature in it, we're basically just drawing from an uncorrelated Gaussian and then warping our draws into the shape of a funnel. And you get much, much better results that way. A lot of the time, if you're doing this, you'll get this result, and we're going to talk about convergence criteria tomorrow. You won't even have any idea that you've missed anything, right? All of your convergence checks might look fine, but there's this narrow, important region of parameter space that's going to strongly influence your estimate of the posterior mean and spread that you've completely missed. So off-centered, or sometimes called non-centered parameterization. So again, just a term I want to make sure you guys have all heard. All right, and then one other thing I want to make you all aware of is that, so far we talked about doing everything where you're fitting all of the individual members and the population simultaneously. About 15 years ago, David Hogg and his collaborators worked out this very clever way of doing hierarchical modeling via importance sampling, where effectively what you do is you just choose some broad temporary interim prior for each of your individual members. You fit the individual members independently, and then after the fact, you re-weight those posterior samples based on what your prior could have been. So it's kind of like you're updating your prior after the fact. This is a technique called importance sampling. We're going to also talk about this in more detail tomorrow. But it's essentially you're just taking the likelihood and updating the prior by weighting it compared to whatever your broad interim prior was. And as long as that interim prior is weak enough that you can sample from the full allowed posterior space, you get equivalent results to if you had fit everything simultaneously. So you can imagine if you're doing hierarchical modeling of thousands of objects, it would be very computationally intensive to fit thousands of objects simultaneously along with your population. But what you can do is fit them all individually and then post hoc update the priors, you get this hierarchical model. So that's, again, I mostly just want you guys to know this technique exists. We're not going to work on it in the problem set today, but you'll have heard of it. And if you start to use hierarchical modeling in your own work, you'll know that you can come back to this. Okay, so we're right at time. So I will leave you with some further reading. These two blog posts are how I first started learning about hierarchical modeling. They're great. Thomas Wiecki also writes a whole bunch about HBayes, so he's another great person to follow. And then, I've mentioned mostly these other people. Yeah, I've mentioned these other people before. Again, they're great resources for anything related to Bayesian modeling. So I'll leave it there and take any questions. Any questions? I know we had a lot of discussion as we went through. Yeah.
So when you're doing hierarchical Bayesian inference, how much does your choice of hyperpriors end up affecting your downstream bits?
Meaning, how much does the functional form of the hyperpriors matter, or how much does like the inferred value of the hyperparameters matter?
So, like, for example, if your prior distribution that you're optimizing is like a normal distribution, right? You'll have some kind of hyperpriors on like mu and sigma, right?
Yeah.
How much does that choice, for example, how would that affect the prior, the optimized prior, which would then downstream affect the
Right. Hopefully it doesn't affect it too severely, but that's something you should always test. Just try different functional forms for the prior and the hyperprior, and then just plot your results from one choice against your results from another choice and make sure they agree to within whatever metric you decide is agreement. 1 sigma is our usual, but yeah. Other questions? Yeah.
What would happen if we try to do like hierarchical Bayesian modeling of a problem or of a population where like the different schools or different districts behave different? So there's really no correlation between them. You can,
Yeah.
which posterior would you find? Will it be uniform or?
It's really going to depend on the data that you have and how severely the actual data generating process differs from your model generating process. But it's, in some senses, no different from any other modeling problem you have, where if you're making modeling assumptions that don't match what's actually going on, you're going to get some biased results. So this is where domain expertise comes in, right? The more you know about, whatever you're studying, whether it's planets or supernovae or dark matter or whatnot, you can use that to inform the structure of the model that you build. Yeah. If any of my answers seem like unsatisfying, the takeaway I want you all to have is that model building is messy, and there's as much art to it as science a lot of the time. So, I know I keep repeating myself, just try a whole bunch of stuff, see if it all looks kind of like it's in agreement. And if it doesn't, then be concerned. All right, well, why don't we, unless there's any other questions, why don't we take a break and then we'll come back for the problem set.
Yeah, let's take just a 5-minute break. Yeah. Start the problem set.